I have shown you in previous videos that if you have a single charge, like my electron here, and I want to find the magnetic field at some point around or near this electron, I can use Biot-Savart's law for a single moving charge. Okay, the constant Q1, the velocity of the charge, the cross product with the unit vector divided by the distance between the source and the observation location squared. This will give me the magnetic field at a point, say here, the magnetic field that this charge creates at the observation location. Now, here's the thing though. If I have a wire and I connect this wire with a battery, with the power supply and the bulb or a resistor or a capacitor and so on, I will end up having a current in this wire. And when we say current, typically this means a lot of charges, in particular, a lot of moving charges, not just one. Now, so this would mean that I got that electron moving, say this way, and this is moving that way, and another one moving that way, and plenty more moving in the same direction. Many more. Okay. Now, I know that if I have more than one charge, then what I need to do is use the superposition principle and say, that's fine, you have more than one, just find the magnetic field that each one of these creates at the observation location, and then just add them all together. Say B net at the observation location, let's be consistent, B net at 2 will simply be the magnetic field that charge 1 creates at the observation location plus, let's say, so if I call this, let's call this obs, okay, so that I'm consistent with the numbers. The net magnetic field at the observation location will be the magnetic field that charge 1 creates at the observation plus the magnetic field that the charge 2 creates at the observation location plus the rest of them. And we can do that. If we want, we can do it. Now, the thing is, we have worked on this problem on using the superposition principle to find the net magnetic field created by a current. And if you work out the theory, it's not that complicated, but it does involve a little bit, really few calculations. But I'm going to skip them. I want to show you the final result and the big picture of this process. If you do use the superposition principle and you simply take this and essentially multiply it with the number of charges, you will find, or you can show if you want, that the magnetic field from a number of moving charges, not just one, those charges that you have in a short length of current carrying wire, can be calculated using this expression. And I will talk about what this is. This is for essentially for a lot of charges. This is in very simple terms, but I will describe it more accurately as if you have a very short length or piece of a current carrying wire. So how can you prove this expression? Just take this and multiply it with n, the number of charges that you have at that location, and then you will get this. Now, what are all of these symbols? That's the constant 10 to minus 7, the same constant as before. I1 is the current, the conventional current that you have flowing in your wire, like this one. And let me show you what I mean by a short length of wire. So let's do, so this would be a short length of wire, and this would be the conventional current, of course, would point in the opposite direction than the direction of the electrons. But this would be I1. It's pointing this way. It's a number. I'm just using the number for the conventional current. Delta L1 will be the vector that points in the same direction as the conventional current, and it has a length equal to the length of your piece, the small piece that you're looking at. Okay. It's a short length of a current carrying wire. That's why I'm using the symbol delta. So make sure that you use a short piece of wire. Now, the rest of it is r hat from the source location to the observation location. And I'm going to treat the source to be the center of this piece. And this vector r needs to point from the source to the observation. Okay? So this expression applies when you have a lot of charges moving in a wire, and if you know what the current is, and you know what is that small length of your small piece of wire, you can use this expression to find the magnetic field at the observation location. Now, at the end of the day, if you really, really want to, even though I don't recommend that you do it, if you really want to, you can take Biot-Savart's law for a single charge and use the superposition principle to do it. It will take a ridiculous amount of time. This is what we always use if we have a current flowing in a wire.